Activity 13-2 bubblers. A bubbler system is installed in the top of a vessel for measuring the level of the liquid in the vessel. The vessel contains a liquid of specific gravity 1.1. A single leg manometer is used to measure the pressure. Single leg manometer sizes of 10 inch, 15 inch, and 20 inch, and manometer fluids with all these different specific gravities are available. So they're going to want us to pick one. Alright, so what do we have going on here is your classic bubbler. So we've got instrument air over here at some pressure, say 20 pounds or something. Then we're going to regulate the air pressure down, and there's going to be a needle valve of some type to administer the air. The air is going to flow down this tube. Now it cannot flow down this leg because that's a dead end, and here's an electronic differential pressure cell with a valve to close it off. So here comes the air. It can't flow down this leg unless the pressure is so high that it forces the working fluid of the manometer up through this vent, and we don't want that. So the air comes along and then it goes down this tube and bubbles out the bottom. Now the pressure at the bottom of this tube is going to be equal to the height of the fluid times the specific gravity. I looked in the answer key and they used 20 feet for the height. That's kind of a worst case. That's nice and safe. Legitimately you could say that these bubbles are coming out here at 19 feet and 10 inches. So question 1, what is the maximum pressure to be measured in water column? Well, that's just what we've done here. So pressure equals 20 feet, but it's not water. We would just say 20 feet of water column if this was just water in here, but it's denser than water, times 1.1. That works out to be 22 feet of water column, and we know that 12 inches water column is the same thing as 1 foot water column. So I'm just going to take that and multiply by my 22 feet of water column, and these units cancel and I'm left with inches of water column. And for number 1, the answer is 264 inches water column, or you could write it as inches water column, either way. Now if we use the 19 foot 10 inches, I'll just take 19 times 12 plus 10. You end up with 238 inches of liquid times 1.1, and that pressure is 261.8 inches water column. So somewhere in this range. Those are both reasonable answers. The book uses this one. Part 2, it says select the best combination of manometer and fluid for this application. So there's a large number of potential combinations here. We have 3 different manometers we can pick from, and 5 different fluids. So that's 15 different combinations. Now let's just start with the biggest one and work our way down. So if we say that we have 20 inches to work with, 20 inches from the lowest level of the working fluid up to the highest level can't be more than 20 inches. So we're to say this is 20 inches. I can look at these other numbers and right away see that both of these numbers are far larger than 20 inches. The pressure here is going to equal the height times the specific gravity. The height's only 20 inches. A good way to see this is just to equate the pressures. So let's just use this one. So the pressure equals 264 inches water column. And that's got to be equal to the height times some unknown specific gravity fluid that we haven't decided on yet. Now I can put in three different values, 10 inches, 15 inches, or 20 inches. And I have 5 different choices for this. So let's say 264 inches water column has to be less than or equal to 20. And I said it's less than because once this is greater than what's on this side, the fluid's going to be coming out the vent. You know it has to be at least 10. And this is getting real simple all of a sudden because we only have one potential fluid that has a specific gravity greater than 10, and that's mercury. So 13.6 times 20 is 272. 272 inches water column is less than or equal to 264, but not a lot of extra margin there. So the answer is we need to have the 20-inch manometer, 20-inch model, and we want to use mercury. Alright, so let's look at question 3. A manometer can be scaled, show the actual level corresponding to the movement of the manometer fluid in inches of manometer fluid per foot of liquid in the vessel. Design a scale for the single leg manometer and fluid in question 2 to represent vessel level in feet and tenths of a feet. Okay, let's do this one little bit at a time. So the first thing is we know that the pressure equals 264 inches water column. Next we know that our specific gravity equals 13.6. So therefore P equals H times specific gravity. We know this, we don't know this, we know this. So at max, when the vessel is completely full, how many inches of mercury are we going to read? And it's completely full when it's at 20 feet. We have 264 inches. I'm writing it both ways. Inches water column, and we have 13.6. That works out to be 19.4 inches mercury. So this would be inches water column per inch mercury also. We have 19.4 inches of mercury on here when we have 20 feet of liquid in the tank. 19.4 inches mercury, and that's for 20 feet of specific gravity 1.1 fluid. And if we do that, we're going to have inches manometer. The units are going to be inches on a manometer per foot liquid. Oops. So 19.4 divided by 20, 0.971. So each foot of liquid we get 0.971 inches on the manometer. If we wanted to know the other way around, 1 inch manometer fluid would correspond to, we could just take the inverse of that. Alright, let's look at number 4. The DP cell is added. The DP cell is added to the measurement system so that the value can be transmitted to the control room. Calculate the DP cell calibration range. Well, that's really simple because we have all the answers. The minimum pressure would be, let's just look at our picture here for a second. What's the minimum pressure? Well, that's the high level in the tank. The minimum pressure is when the tank's empty, which means that this is atmospheric pressure, and if this is empty, this is atmospheric pressure down here. That means this side of the DP cell is at atmospheric pressure, and this side of the DP cell is at atmospheric pressure. So 0 is the bottom of the range. And when the tank is at its maximum level, we're going to have our 264 inches of water column pressure that we calculated. And note that 264 inches is more than 12 times this number. That would be 240. So if this were water, it'd be 240 inches of water column, but it's not water. It has a higher specific gravity. So we're going to just use that 264 as our upper limit. So there's the range. 0 inches to 264 inches water column. Okay, that's it. Have a nice evening.